rolling with just the four of you. So, um, I guess yesterday was the kind of an introduction to weather and getting our feet wet with weather. Um, we're gonna talk about some of the other things with weather. Kind of talk about altimeters and how things work in general. I know you guys got some of that yesterday, but we'll go through the advisory curricular about weather, and then we'll start looking at some charts and just getting familiar with weather. So, as we've stated before, weather is a huge part of our job. Um, it affects pretty much everything we do. Uh, every morning, as a dispatcher, you go in and you actually do what we call a weather brief, where you just go through and you're looking at what's going on over the entire United States, parts of Mexico and parts of Canada, and just getting a sense of where problem areas are, because there's it can vary so drastically day to day. My brother today went into work and had a couple diversions in Chicago and O'Hare airport, and then also in Detroit, because the weather, just tanked this morning and dropped down below an eighth mile. So, I mean, weather can happen fast and without warning. And we do a pretty decent job of um, figuring out and forecasting weather in general, but um, things change so rapidly that it's hard to really predict it as well as we'd like to. So, um, we have put in in our lesson plans. Once again, we've put in the advisory curricular that we want you guys to get familiar with. We're going to go through it tonight, but this is always good to go back to and just kind of read through and just kind of further your understanding of how everything works. So, one of the first things that we're going to talk about, yeah. Somebody sounded like somebody was talking. Anyway, so one of the first things that we're going to talk about is our atmospheric pressure. So, pressure, altitude, and density, altitude. We kind of talked about them 2 classes ago when we were talking about the, how drastic of an effect high temperatures and um, high altitudes can really affect the performance of our aircraft. We talked about Phoenix and how Phoenix during the summer, just because of the heat, can actually stop us from being able to fly because our aircraft just won't perform and get off the ground like they're supposed to. So when we talk about pressure, we're talking about directly relates to the performance of the aircraft. It also relates with the instrumentation inside the aircraft. If we don't adjust our pressure in the aircraft, then we won't get an accurate reading on our altimeter, and that could cause a lot of problems for us, especially when we're flying through mountainous terrain. Um, so we'll go through how we calculate, just kind of the general stuff about air pressure here. So let's start off with this. Atoms and molecules that make up various layers of the atmosphere are always moving in random directions. Despite their tiny size, they when they strike a surface, they exert pressure. So each molecule is too small to feel and only exerts a tiny bit of pressure. However, when they add the pressures from a large number of molecules that strike the surface of each moment, the total pressure is considerable. This is air pressure. As the density of the air increases, the number of strikes per unit of time and area also increases. So we can kind of see this here. The air molecules, basically equal weight. So the more dense our air gets, the more pressure it exerts. Those molecules are moving faster and hitting each other, generating that energy. So when we talk about the barometer, we're talking about measuring how much air is in a given area. So there's a scientist that invented this instrument called a barometer that measures how much pressure at any given point we're feeling generated in the air. So as you can see here, this is kind of a really basic breakdown of a barometer, and we can see it measured in the barometric pressure. A lot of people, I don't know if you've heard anybody say, well, the barometer must be dropping because they can feel it in their body and stuff like that. Well, there is a little bit of truth to that.
I've never heard about that before.
You haven't heard that?
Well,
It's
no, like I've never heard that it can like affect your body. Like I don't know how that all works.
yeah. I don't know how it all works because I honestly can't tell. But there's, I don't know, maybe it's a thing with older people that I've heard. But
If you have any metal in your body, then you'll be able to know. So if you've had any surgeries, like I had knee surgery a long time ago. I've got several titanium screws in my knee, and I can feel it when there's a storm coming in. But yeah, that's what most people say. Like if they've had any, like it's really more related to like if they have like any, non-human parts to them, that were put in via surgery or anything like that. It usually will affect your joints and things like that, or areas that you've had operated on.
yeah,
Interesting.
yeah, it is. I know people that they can. That's one of their complaints is when a storm cell's moving in, like before it even gets cloudy, they can actually feel it, and they're like, "Yeah, the storm must be moving in because my joints are swollen and achy or whatever." It's really weird. Um, but yeah, at any given point, that barometer can fluctuate a pretty significant amount. Um, uh, we see huge fluctuations, especially in the summertime, where you have a really hot, day, and then it gets a thunderstorm rolls through and cools the area significantly. It really changes that the barometric pressure. Um, but we each have in our aircraft, our altimeter basically has we our altimeter uses the barometric pressure to um, to tell us our altitude. So it corrects the altitude according to the barometric pressure. Um, so the way that this measures it is in what is it called? Millibars. Um, we also have like hectopascals or inches of mercury, or psi. So each one of those are common units of pressure that we use. So as you can see here, this is how we in aviation tend to measure our pressure. This is the barometric pressure that we need when we're flying, is inches of mercury. So so what happens is, as this rises, to 30, 31, 32. I mean, I've never seen it go all the way to 32, but as it rises per tenth, well, even less than that, it will get better performance out of our aircraft, because that means the air is getting more and more dense. There's more air for our aircraft to use. As we get the other way, it's basically meaning that there's less air molecules in a given area. So we actually get worse performance. So when we talk about station pressure, you have down here at New Orleans at sea level, their standard pressure is 29 or 9 or 2. So that's what we call standard sea level pressure. Or, yeah. But in Denver, because of the altitude, their standard pressure, like the equivalent would be a 24.92. Does that make sense?
Yeah.
We still measure everything off of the standard sea level pressure, but this is just telling us, the pressure measured in an airport. So pressure is lower at higher altitudes. Therefore, the airport with higher field elevation usually have lower pressure than the airports with lower field elevations. So, yeah, and the things that can change that, like it says here, pressure variation. Atmospheric pressure varies with altitude and temperature of the air, as well with other minor influences such as water vapor. So all of that plays a part in that pressure. So, as you guys probably learned in some of those videos, the higher there's, I'm trying to think of whether or not it goes over this in that big video, but basically that longer video you guys watched. But basically, as we rise in elevation, we have what's called lapse rate, where we measure standard differences in temperature and pressure as we increase in altitude. So as we get higher, like it kind of, as we went over with station pressure, the higher you get, the less pressure there is in the air. And I talked about it. I kind of compared it. If we were to just drop feathers into a tube here, and then you were to go through, say this was this picture right here, was a tube.
I got a question about what you said. Now, so you said that the higher you get, the less pressure there is in the air. But I always thought that the higher you get, the more pressure builds up. Like, because I've heard stories where, like, if you were to, for example, open a window at such a high altitude, your head would burst or whatever. That's just what I've heard.
Yeah, so that's when we talk about the pressure changes with altitude. Here, just 1 second. I need to change a setting on my mouse really quick. I'm going to make it big again for you guys so you can see what's going on. So what they're talking about there, and I'm just going to spend a little bit of time on that. What they're talking about with the pressure, say you're in an aircraft and all of a sudden there's a depressurization. What happens is the aircraft is pressured as if it were at 10,000 feet, but you're at 35,000 feet. So that rapid change in pressure is what causes the issues with our body and stuff like that. It's an extremely rapid loss of pressure, and that's what causes that rapid, that's what causes the issue with like an airplane, losing pressure. But my gosh, why can't I find this right now? There we go. So that's the problem, and it's the same with like a spacecraft, right? Like think about being in outer space, and if say the skin of their space station was to get hit by a rock or something, what would happen is the pressure is far greater inside the aircraft because of the amount of air molecules in there, that it basically would collapse the spacecraft due to that rapid loss of pressure. So the important thing here is with the pressure is like, think about, have we talked about what makes up the atmosphere? Like how much oxygen, how much nitrogen, and stuff like that?
Don't
it
we
was
have
in the video
less?
that we watched.
Okay. So what percentage of the air that we breathe, what percentage of that is actually oxygen that we're breathing in?
Isn't that like 6% or like way low?
It's not quite 6%, but it's only like 21. I believe it's 21%. Now this is something that you're going to get asked on your oral. I guarantee it.
Oh yeah, it's 20%.
But yeah, it's a very small amount that's actually oxygen. Well, none of that changes in our atmosphere. No matter where you measure that air, you'll have that same percentage of nitrogen, oxygen, argon, and the other gases in the air. But what happens is, as we rise, and I think it shows it here, as we rise, basically those air molecules spread further apart, which is the problem that that's why the oxygen masks drop from the roof of the airplane and everything like that when there's that depressurization, is because we're still getting the same percentage of air into our lungs. There's just not as much of it. There's not enough to supply our body with it. So we need that oxygen supplement to breathe in, because that's like compressed. It's a lot more that's going to allow us to continue to function. It's kind of fun. Let me show you a quick video.
Just real quick, you said how much oxygen do we breathe in that, or how much was it again?
Let me pull up my percentages here.
Okay.
Let's see. So it's 78% nitrogen, 21% oxygen. And this is, everybody write this down really quick because this is something that you guys have to know, and it will be on a test. But yeah, so 78% nitrogen, 20% oxygen. It's like 0.9% argon, 0.4% 0.04% carbon dioxide, and then we just throw the rest of it into a lump sum of like other gases. But
How much was the argon again?
the argon is 0.9%. Let's see if I can.
Sorry if you can't understand me.
No, you're fine. You're fine. No worries. Oh, trace gases is the other one. So there we go. That's the one that I'm looking for.
And this is and then this is what we breathe when we're at a certain altitude. You said
Any
about the 21%
altitude, any altitude, no matter where you are.
Okay.
In this atmosphere, this is what you breathe in. So let's see if I can zoom it in here. So there's your 78% nitrogen, 21% oxygen, 0.9% argon, 0.03% carbon dioxide, and then 0.7% of trace gases. 0.07% of trace gases. So at any point in the entire atmosphere, this is the amount of or those percentages stay pretty consistent. But what happens is because there's less pressure, that means that there's less air molecules in the air. And so that being said, if you try to breathe at higher altitudes, basically you're just not receiving enough of that oxygen to allow your body to continue to function. Let's see. So the military, for air crew, they actually make their pilots go through and actually feel this. So here you can see him functioning normal. He's looking at cards and holding them up and saying exactly what he's holding up. Pretty simple task, right? Well, what they do here is they're going to increase the altitude in the chamber. And you can see without his oxygen mask on, that simple task gets really hard to do. Let's see if, can you guys hear what he's saying?
No, we can't.
Okay. So,
do you just want to send us the link and we can watch it real quick, or?
Yeah, we could do that. anyways, let's see.
I almost went on one of these. I was really excited to do it, but I didn't get to go on one.
Yeah, but they make their pilots go through this training. So the link's in the chat. But they put them in these hyperbaric chambers, and they can make it as if they were at 30,000 feet, and basically they make them remove their mask and see the effects of high altitude pressure loss. So watch that video really quick. Kind of interesting, huh?
That poor kid.
Yeah, they make all their pilots, even all the air crew, anybody that's going to be in the aircraft, go through that training, because you need to be able to recognize what's going on. But at the same time, you could tell that He didn't know. He had absolutely no idea. So that's why.
And then he went like right back to normal as soon as they put his mask on him too.
Yeah. Yeah. I mean, they were asking him, like, or they were telling him, look, put your mask back on. You're going to die if you don't get your mask back on. Like, but there's actually stages of euphoria that you go through in a pressure loss situation where it's like nothing's wrong. Everything's just happy. He had no idea what was going on around him. He was just doing the task he was told to do, but even then, he wasn't even doing something simple correct, you know. So, and you could hear him. They're like, "Tell us your symptoms." He said, "Oh, I feel tingling in my toes," and then all of a sudden, he just lost his ability to reason or to process simple things. So that's what happens is those air molecules get more and more spread out, and then even though there's the same percentage of oxygen there, it's just more and more spread out. And that's the same with performance on the aircraft. The aircraft, when it's at that higher altitude with those air molecules being more spread out, like especially in a like a propeller-driven aircraft, what happens is when there's just nothing there for the aircraft to bite onto with the propeller, the engine really lags. So can be a really dangerous situation. So so you can see here in this graph, as I was telling you about before, is this cold air in the winters, the air tends to be more dense and more stable. And so our barometric pressure, our inches of mercury that we're reading basically gets higher. So it goes from a 29.92 to like a 31 or better. And so that's that's cold air. Now in the summer, it's quite the opposite. What happens is that pressure, the air molecules move faster and spread out, and there's just less air molecules around. And so, that being said, as we talked about, it greatly affects the performance of our aircraft. So, we talked about this sea level pressure. And our standard sea level pressure, the important thing to remember that I want you guys to know is that the sea level pressure, standard sea level pressure is 29.92. So I want you guys to know that. So you guys have looked at the weather charts, watched weather and everything, right? On the news at night. Well, we're going to figure out what all of that means that they're talking about when you're watching the news. Let's see if I can make this a little bit bigger.
Yeah, it's those lines that I don't understand. But.
Yeah, and that's what we're going to talk about. So when we look at these charts, what's happening is we have, if you've watched the news and stuff, you've watched talk about high pressures and low pressures. Okay. When they talk about these high pressures and low pressures, what they're talking about is the area of a high tends to be more stable, whereas an area of a low is less stable. And so what happens is you have these high areas that are constantly pushing and trying to overtake these low areas of air. And these lines and the H's and L's are the different pressure systems. So you have these fronts, these are called cold fronts, and then where you see like that purple up top, let's see if we can get it to stop right there. Okay. You can see these, you know, we're going to get a little more into this, but you have squall lines, you have cold fronts, you have warm fronts here, you have occluded fronts, you have troughs. And these maps just show us where that pressure is going. So when we look at these areas of low and high pressure, kind of something that tends to follow these lines of pressure and these fronts are things like the jet stream and weather. That's where we start seeing these areas of weather. Kind of as you see, like right here, you know, we've got a low and a high basically ramming into each other, and you can see all the weather that's forming here. So, so we'll get into that a little bit here. So, when we look at these surface analysis charts, that's what it's showing. It's showing those lows, highs, troughs, the ridges, and so as you can see here, low is a minimum of atmospheric pressure of 2 dimensions, closed isobars on a surface chart, or of a minimum height. So the contours. So you can see on this chart, these are called contours, right? So these are called isobars, and then you can see the contour when they get closer together. That's an area of low pressure, but when they're more spread apart, you have the high pressures. As you can see, very well represented here in this part. You have a lot further separation of these isobars, and you have a high pressure system right here. So so a high pressure is a maximum of atmospheric pressure in 2 dimensions on a surface chart, or a maximum height of closed contours of a constant pressure chart known as an anticyclone. So these pressure systems actually rotate, and we have cyclonic action, then we have anticyclonic action. Basically, a cyclonic action is oh my gosh, I'm having a brain fart. Man, trying to think.
Do high pressures and low pressures spin in the same direction?
No, and that's what I'm trying to get right here is low pressures. Yeah, low pressures are cyclonic, and then high pressures are anticyclonic. So they're rotating in opposite directions. So yeah, so cyclone is a clockwise rotation of air, and anticyclonic would be um, a counterclockwise rotation. And as we look at this chart, you can kind of see, like I said before, when those two movements of air basically collide, we tend to see that weather, that high and low kind of hitting here. That's where the weather tends to generate. So when we talk about a trough, so this on this chart would be, these are the troughs. Okay. So it's like it says, an elongated area of relatively low atmospheric pressure. So think of a trough as like a trough, right? It's just that really long area of that low atmospheric pressure. And then a ridge, as you can see here, is an elongated area of relatively high atmospheric pressure. So this is kind of what we were looking at, right? So yeah, I mean, this just kind of demonstrates those, what we were just talking about, the highs and the lows. And then as you can see in the areas of the low, you have the isobars closer together like that, and you can see the trough where it's just a really long section of that low pressure. Whereas with the highs, when you have that really high pressure and it just elongates like that, you get those ridges. So you can see here where it's just that really long area of low pressure on this map. So we have, so that's the surface analysis chart. We also have a upper air chart. We call these prognostic charts, but it's basically the same information that it displays. Just those highs and lows, but just at a different altitude. So I've got a video for you guys. Let me see here. This goes through the altimeters a little more in depth, help you guys understand them. So watch this video and we'll jump back on in just a second. to ensure that they're flying at the correct altitude, you have to get the weather report from the station and basically calibrate your altimeter. So we have a couple different definitions of that altitude. We've got true altitude, which is basically your actual altitude. And then we have an indicated altitude. They aren't always going to be the same, right? If everything were hunky-dory and standard pressure all the time, and everybody was tuned in at 29.92, they'd all be reading the same altimeter. And that's actually what pilots do once they reach that Class A airspace, is they actually go to the standard altimeter, because regardless of what the pressure is, everybody's in that same pressure. Does that make sense? And so they're all flying at the altitude they're supposed to be. Now, that doesn't mean that they're flying at a true altitude of 41,000 feet necessarily. But what it does mean is that everybody's on the same page. And so you don't have to call into the station every time, you get over a new station and change your altimeter setting. It'd just be way too much for the pilot to do. But it does allow everybody to stay on the same page there. But when you're talking about lower altitudes where terrain is much more of a factor, what happens is and think about like when you're flying your little Cessna 172 at 80 miles an hour, you're a lot more likely to be affected by that altitude, and your altimeter does have to be correct. It's taken us a longer time to fly over those different isobars and those different levels of pressure, and so it's not as much work for somebody flying lower, but at the same time, not only that, you are affected by that terrain a lot more, especially in places like Utah, where there's high peaks all over the place. There's radio towers all over, things like that. If we're not making sure our altimeter's set correctly, then our chances of having or being involved in an accident are greatly increased. Especially when we're flying like approaches into airports and things like that. We've got to follow that profile. So yeah, but this chart just kind of, shows you the difference. And as I said before, density altitude and pressure altitude are directly related. So if we get that colder parcel of air, that lower pressure, our air is also more dense. So if we go from a higher pressure to a lower pressure, our altitude goes from 10,000 feet to 9,000 feet. But if we go from a low pressure to a high pressure, our altimeter is going to increase. Does that make sense with everybody? It's super confusing. At least it was for me going through my training.
I think so. The picture makes sense, at least.
Yeah. So
that visual is good for it.
So yeah, what this picture kind of indicates is like if everybody kept their altimeter at the same setting, depending on whether or not they're in like a standard temperature or standard pressure, or they're in a lower pressure or a higher pressure. Regardless, their altimeter, this is the difference in altitude. I confuse myself even talking about it. And so this visual helps with that as well. So what happens is when you're flying along, now just because you're in a lower amount of pressure of air doesn't mean that, all of a sudden your plane drops to that lower pressure of air. What it's talking about is when we're flying, we're trying to maintain a specific altitude, right? A lot of times air traffic control will call up and assign us an altitude. They'll say, fly at 6,500 feet following this route. So when we fly at 6,500 feet, if we're not changing our altimeter, we're going to try to keep the plane at 6,500 feet because we don't want any traffic problems. We don't want any terrain problems. But as we don't adjust our altimeter and we continue flying, say we go to a lower altitude, well, because we're trying to keep our altimeter reading 6,500, basically we start flying the plane lower and lower into the ground we're kind of chasing that needle. Does that make sense? So that's where the issue is. So now when we throw in our temperature here, it also starts affecting the air pressure and density. So that's basically what it goes over. And we're going to talk lapse rates and stuff like that, but there's kind of a standard that we use when we're planning flights. So I'm going to pause it right there, and we're going to do our dinner break. My dinner just came, so all right. Is everybody back?
Yes, sir.
All right. So going back to density altitude, I mean, this is all stuff that we've talked about multiple times over the last couple of classes. And we watched a video of exactly this, right? You can see what effect it has on takeoff roll. Whereas this guy's getting up to about 1,200 feet in this distance at 1,300 feet per minute. At 5,000 feet, same airplane. Look at virtually adds on about 3/4 or a third of the distance onto his climb, and then he's only climbing out at about 1,000 feet per minute. Not going to clear those mountains. So it's kind of a rough example of what it's doing there. So we're going to talk a little bit about winds here. So talks about like the pressure gradient force. So, the high's pushing to the low. We kind of talked about this. High's trying to overcome the lower pressure. So, I don't know. A lot of this you might have to go back and read if you want a better understanding of it. I'm just trying to pick out the high points of things that we want to cover that are going to be most applicable to you guys. I don't want to overload you guys with too much information. Was it you, John, that was saying that you were in the Army? Oh, looks like he left. Anyways. Yeah, talk about the Coriolis force, which is basically the effect the rotation of the Earth has on our winds. So these are just areas of the deflection. So this kind of shows you what happens, in flight, the effect that the Coriolis effect would have on us. If we're flying south, then the effect of the Earth would be to deflect us a little more to the west, and so on. Talks about just the magnitude, the variation that happens with wind. So more wind, more force. Kind of easy, self-explanatory, right? Got friction force, got, once again, a lot of this stuff is just not too pertinent to you as a dispatcher. A little more pertinent to pilots, but not as pertinent. So here you can see the rotation that we were talking about, right? High pressures. We have a clockwise rotation. That would be cyclonic, and then a low pressure rotates in an anticyclonic or counterclockwise rotation. Let's see. So you can see here the difference between these cells. So we have polar cells. We have what are they? The tropical cells. But basically, as air rises, it diverges and travels towards the poles. Once over the poles, the air sinks, forming the polar highs. At the surface, air diverges toward the outward polar highs. Surface winds in the polar cell are easterly. So basically is showing that here. So you have these cells, and what happens is air wants to rotate in a specific direction depending on where you are in relation to the Earth. You can kind of see that when we look at, let's look at this is what we call a winds aloft chart. So you can kind of see those circulations on these charts. Let's see if we can zoom out on that picture a little bit. Pretty much just covers the US, but anyways, you can see that the air tends to flow in a west to east direction over the US. And you can see that it kind of has a swirl to it, right? A cyclonic or action to it. As it comes out here towards the poles, it's going to turn up this way, whereas this cell of air is going to rotate down this way.
Doesn't every line on those weather, doesn't every line represent 10 knots?
Good question, and we're going to get into these charts a little bit more. But these lines here, these flags, the shaded flags, are 50 knots of wind. The longer lines are 10 knots each, and then these shorter lines are 5 knots. So if you look at one of these charts, like here's 100-knot wind, right? And when you read this, this is the direction of the wind. So think of it as like you holding a string out in the wind, right? This is the direction of wind. The wind's coming, or the wind's going from west to east. And so these flags just indicate that speed at which the air is flowing. So the winds here are coming from the north going south, and then coming more that west to east, and then once again going from south to the north. So, but yeah, we'll get a little, or we'll get pretty heavy into these charts because we've got to understand these charts and how they apply to us when we're dispatching. So what's the jet stream?
Isn't that the strongest wind? Like it pulls wind the most.
So it's like a really high speed column of air, right? So we can see jet stream will move. It's not like one particular area, but the jet stream will move areas. You can kind of see it on this chart here. I mean, this isn't a jet stream chart, but you can see where the jet stream is going to be, most likely be. But yeah, you can see these higher winds, and they continue to accelerate through this part of the country, and then yeah, you can just kind of follow that on this chart. Whereas down here, the winds are a lot slower of a speed. There's actually a jet stream chart. Let's see if I can. So this shows us where the jet stream's at. Just tells you the speed. So flight level 300, okay, 30,000 feet. You can see the jet stream, 70-mile-an-hour winds through this area. You can see a 90 to 110, and then 130 to 150. So really nice when you're flying, from Southern California up to Chicago. You have that really nice tailwind that's going to get you ahead of schedule,
And save fuel.
Yeah, not so fun coming back the other way, though. But yeah, so jet streams are relatively narrow bands of strong winds in the upper levels of the atmosphere. The winds blow from west to east, but the flow often meanders southwards and northwards in waves. So you could kind of see that on the chart, right? You can see these waves, and you can see the variation. It'll go southward, but then northward up there. So jet streams follow the boundaries between hot and cold air. Since these hot and cold air boundaries are most pronounced in winter, jet streams are the strongest both in the northern and southern hemispheres in winters. So going back to this chart, you can see, the jet stream tends to follow these cells, right? The jet stream would just be this high. You can see these two cells are rotating in opposite directions. So the jet stream is going to, that's where you see the jet stream is is where those cells are basically meeting and pushing, accelerating the winds there. So, yeah, I mean, you can see right there, you got the polar jet and the subtropical jet, as I showed you in this picture here. Polar jet, subtropical. And at any given point, they can be anywhere, like we said before. Just depends on where the polar cell is subtropical and the tropical cells are. That kind of dictates where those jet streams are at that point. So you can notice that as you get closer to the center of the jet stream, the air tends to accelerate. Also depicted here on this chart. So one thing that you got to be concerned about with the jet stream as well is, where do you think the most clear air turbulence lies?
I'm not sure what you mean by that question.
So where do we tend to see the highest areas of turbulence?
Over like a mountain range?
Okay, we have different types of turbulence, and a mountain range can produce a type of turbulence called mountain wave turbulence, but we tend to see, with that kind of turbulence, we tend to see cloud formations.
I would say,
but when I'm talking
high altitudes.
When I'm talking about clear air turbulence, what I'm talking about is there's not a cloud in the air or any indication of turbulence being produced. So that convective activity is what causes the turbulence. When we have areas of really warm spots on the ground, we get a parcel of air that rises more rapidly than the other air around it, right? That's how birds sit there and circle and hover over specific areas. They catch those air pockets of warm air. Well, turbulence is when we hit those pockets of warm air, when we've gone from a stable column of air to a warm, rapidly rising bit of air. That's what causes that turbulence. So when we think of like thunderstorms, we see those clouds gaining altitude really fast, those really tall clouds. But when we talk about clear air turbulence, we're talking about air that there's no indication of turbulence happening. And so typically when we see turbulence, clear air turbulence, they say that 2/3 of all clear air turbulence happens near the jet stream. So that's what that's one thing that we need to be concerned about when we're planning our flights, right? So we don't want to cause harm or injury to our passengers or flight attendants, and we kind of want to predict that turbulence as much as we can. You can see it here. Think about where that jet stream was, and now look at this map. I mean, that's where they're predicting the turbulence. The areas of turbulence are going to be the greatest, right? So it kind of follows that same band of the jet stream. In this chart, you can see yellow means surface, whereas green means aloft, meaning up at altitude, right? These areas point at the pockets that are these different sections and give us altitude ranges. We can also see things like this. LLWS stands for low level wind shear, which are pretty detrimental to aircraft. So, and we've talked about those. So, when we talk about local winds, we're just talking about a small area of basically these two air masses trying to take over one another. Kind of as we talked about before, think about like a hot air balloon, how it rises. The warm air wants to stay on top, right? And so it's trying to overtake those colder parcels of air. Well, what happens is we get this rotation. It causes that rotation. And this is how we see like the thunderstorms form. Is we have this warm air trying, and that's why I also said that's where we tend to see the storm systems, is because we see that the warm air is trying to overtake this cold air. So if you're in this warm air parcel, miles away from that front, then it's pretty consistently that high pressure, that warm air is just, that low, I've been saying high pressure all night. That low pressure of warm air is just sitting there being consistent, like it's just raising consistently. But when it's taking over this parcel of colder air, what's happening is it's cooling the air down at altitude, which is making the air fall and become more dense. And then as it moves across the surface, the wind kind of pushes it across the surface of the earth. As it hits that warm air or warm surface again, it starts heating up again. We see that rotation. So that's where we start seeing those thunderstorms happening, is during this phase of air rising. So like I said before, the local winds can produce aviation weather hazards. Turbulence and shifting winds are common. Clouds and precipitation, including thunderstorms, can develop in the rising air over the warmer surface, given the sufficient moisture and lift. So as we look at that chart, once again, you can see let's see if there's any convective segments. You can see that it's the areas of where lows and highs are converging and those fronts are happening, is where we typically see the most weather occurring. I'll figure it out. Just give me 1 second. Here's that surface weather prognostic chart that we were talking about, the surface chart. You can see right there. This is a perfect example of what we were talking about. Have a high pressure on both sides of a low pressure, creating all this weather. So, kind of interesting to see, right? So,
It's cool that I finally know what all this means after watching the weather for so long.
and we're gonna. This is kind of the science behind it. What is important for us dispatchers is actually reading these charts that the meteorologists actually use to predict or forecast the weather. So this is where we're really going to spend the time when we're talking about weather, is these charts and how to read and understand them. But we're just trying to give you a little bit of the science of how it's created, and then we can move into the charts and give you a better understanding of how it's affecting our flights. So, you literally become a weatherman when when you're a dispatcher, you've got to understand, and there's times where you can predict things are going to happen before a weatherman can, the news even puts it out. Oh, excuse me.
That's good. I was telling Adam yesterday, like, I'm a total weather junkie. Like, I've been stoked for this part of it.
Yeah,
Nice.
it's a lot of fun.
You see that shot?
But yeah, so sea breeze, this is something that we see along our coastlines especially. This is when that cooler water or cooler surface, I mean, water is really cool, right? When that cool air moves over the hot air or the hot land, it generates a whole lot. It kind of creates its own little weather system along our coast. Going back to our charts, you can see how it creates these weather systems over our coastlines, especially our west coast, because that's where a lot of the wind is coming from, is that west to east, right? So areas like San Francisco, Seattle, Portland, LA, depending on the day, you're going to see a lot of these little weather systems just pop up right over, and they're kind of isolated over the coast. Well, that's what we call the sea breeze front. So what happens, like we were talking about, that high, colder air just comes in and it starts pushing this lower air, and as we said before, it creates that lifting action, just like as if it were on land and we had two different, a warm bit of land and then a cool bit of land. It creates that same system. We tend to see a lot of weather, like think about Seattle. That's the area that really comes to mind to me when we talk about sea breeze fronts. Seattle is known for the daily rains that happen every day. There will be 10 to 15 minutes where it's just a downpour, and then it'll just be sunny and bright for an hour or two, and then all of a sudden we'll have another weather system hit, and it'll just downpour. A lot of that is due to the sea breeze fronts and to kind of its own little weather system that it develops there, because you also have the mountain range over here that's kind of helping that entire action. But yeah, you can see here where the divergence is, where you have these areas of weather. So the coastline shape will also help generate that weather. And when we talk about this, what comes to my mind here is San Francisco, because this is kind of, I mean, you think about San Francisco, this is basically what it would look like, looking down on it. Is you have these areas of divergence where, and San Francisco kind of comes out and it generates that the thunderstorms or the amount of fog as well. You have the warm land and the cold air, and when it's pretty stable, it generates that fog at the surface. So it's when we talk about fog, we'll talk a little more about that as well. So this is the land breeze, or so land breeze is when it's the opposite, when the land is a little cooler than the warmer air over the water, and so it creates kind of a reverse cycle of that. So we tend to see this at nighttime, versus the daytime because of the, I mean, you can kind of see this. It's the warm land. The sun is what's warming the the land up more rapidly. Water tends to lose its heat quicker than land, so at night it kind of reverses that cycle. Lake breeze is just like a land breeze, but basically you're getting pinched between two bodies of warm land. See this in Salt Lake a lot. And that's also why Salt Lake is known for the greatest snow on Earth, is because of that lake effect that happens. That's typically what we call it, right? So what happens is the water's cooler, got two bodies of warm land around it, and it creates those systems of rain and snow, and kind of why Salt Lake is so good for snow is because you also get the salt. Not only is it freshwater, but not freshwater, but not only is it, you have that evaporation, but you're also getting the salt in there with it, so it makes it really dry and light snow. But here's an example of that lake breeze, and the system that it creates. Right, that's a really good picture, actually. So, yeah. Valley breeze. We get this a lot in St. George and in Salt Lake, where the wind is, and this is also what kind of makes Seattle so unique and why it rains there so much. Is not only do you have the sea breeze, but you also have the mountain range right there that's helping kind of create a weather system over it. So yeah, this is just basically, once again, the cold air is descending rapidly, and the warm land is creating hot air that's trying to rise up over the mountaintops, while this cold wind comes into the valley and basically forces the hot air up in every direction, trying to escape it, trying to overtake those cold winds. And that's why you see a lot of these thunderstorms and stuff right against the mountainsides, and is because of that valley breeze, and the convective activity that occurs because of it. So, so mountain breeze, you have valley breeze, and then you have mountain breeze, where it's the exact opposite. Just like with our sea breeze and land breeze, is it? It's just the exact opposite. You got the colder air coming down the sides of the mountain, and the warmer air basically coming down the valley. And yeah, basically the same exact thing, just in reverse. So as you can see, there's a pattern here, and what you guys need to remember is that warm air rises, cold air sinks. Warm air tries to take over the cold air, and that when you have warm air rising rapidly, that creates storm systems. So that's the basics of, if you can't tell, that's the basics of weather systems here. that we're trying to cover. Now, the only thing that changes is it the land that's creating it, or is it the water? Is it the mountains that's creating the warm air, or is it the valley breeze? So the name changes depend on that, but the overall thing to remember is just what I said. It's warm air is trying to overtake cold air. Highs are the cold, highs are the low cold air, and lows are that hot rising air. And as they converge, we see the storm systems form on the low, because that's where the convective activity is. That's where the air's getting hot and rising rapidly. So as it tries to take over that lower cell. So this is just talking about Celsius and Fahrenheit and the conversion. I really don't know this myself. I know basically how to get it, but at the same time, I never do the conversion. I'd rather pull up a conversion calculator. But yeah, basically it's just to find out, to convert Celsius to Fahrenheit. You take the degrees Celsius, multiply it by 9/5, and then add 32 degrees to it. That gives you a Fahrenheit. And then Celsius to figure out, do our Fahrenheit conversion to Celsius. Just Fahrenheit minus 32 times 5/9. A lot of our temperatures that you're going to see when weather's reporting, in fact, I think the vast majority of it is going to be in Celsius. When we talk temperature in aviation, it's always going to be in Celsius.
Or am I required to learn that, or can I just use a
The conversion?
Or do I need to know that conversion? Yeah.
I don't know the conversion. Like, I don't have it memorized, and I never once have actually tried to even write it out. So that shows you how often
that works for me. Yeah.
I've got two sides of my brain. One side is when I'm talking aviation, I think of Celsius, and Fahrenheit doesn't even exist. But then when I'm not dealing with aviation, Fahrenheit's the only thing that exists, and Celsius just goes away. I don't know that makes sense, but I've always just done a conversion calculator when I needed to do the actual conversion.
Right. No, and that makes sense, like the way you explained it.
Yeah. But so here's where we start talking about lapse rates, I think. Man, a lot of this is just not all that. You guys don't really even have to know or understand it. So I mean, talks about heat transfers here, convection and conduction, right? And everybody kind of understands that. You got a heat source. Conduction is where the heat transfers. Convection is where it basically stays within a contained space and rotates. So when you put the lid on your pot, it creates its own little convection system. It's just rotation of the air there. Conduction just is where it transfers. Yeah, as you can tell, I'm super knowledgeable about how that all works exactly, but Yeah, actually, I'm not. So, like I said, a lot of this is just kind of like to help you understand where you're going to see weather on these maps and a basic understanding of how it works. Let's see. Oh, here's an important one that everybody is going to have to know and be able to explain is temperature inversion. So we talked a lot about how that low pressure is always trying to overtake the high pressure. The warm air is always trying to overtake the cold air. While temperature inversion is the exact opposite of that, is where a warm pocket of air is sinking below the high pressure is overtaking the low pressure. So you have the really warm air against the ground versus the yeah. Man, I'm confusing myself.
Hold on. So,
Sorry, go ahead, Sarah.
oh, I was going to say, so the temperature inversion is when the warm air is sinking below the high pressure. So regular is where the high pressure is trying to take over the low pressure. Did I get that right?
Yeah, so
high pressure normally tries to overtake low pressure.
Yeah, so the high pressure is trying to. So this is how normal weather happens, right? You got a low pressure that's overtaking a high pressure, trying to climb a warm pocket of air. Yeah, just a second. I'll tell you exactly what I want you to write.
Okay.
So, normal situation, you have hot air trying to overtake cold air. Just think of it as that. The hot air is the low pressure. The cold air is the high pressure. On a temperature inversion, it's the exact opposite. The cold is overtaking the warm. And so you see this in like Salt Lake, where the cold air will move in over the valley and trap the warm air below it. And
okay.
And what happens is that warm air just sits there and circulates, and it's just it's trapped, right? It's trapped under that pocket of cold air, and that's why like you get all that pollutant and the air quality is just horrible in Salt Lake, is because basically that warm air has nowhere to go, and so you get all the nasty crap in there until you have a storm or something come in, or high winds come in and basically reverse it back to the way it's supposed to be.
All right.
So what I want you to write down.
I don't know why that confused me. I'm sorry.
Probably because I'm trying to explain it and I'm confusing myself while I'm trying to explain it. Because like I said, I'm visual, so I can't really explain it unless I'm visually picturing it. So I'm trying to make it all work in my head before I communicate it, but it just comes out as a mess.
I know, I feel you. I'm the same way.
But this is what I want you guys to write. A temperature inversion is when a low moves under a high pressure. Or when a cold pocket of air, or cold air overtakes a warm pocket of air and traps it. That'll be completely adequate and sufficient.
Sorry, did you say temperature inversion is when a low moves under a high pressure, or when a cold pocket of air. What?
Overtakes a warm pocket of air.
Thank you.
So let's see. So here's what the advisory circular says. A temperature inversion, or simply inversion, is a layer in which the temperature increases with altitude. If the base of the inversion at the surface is termed a surface base inversion, if the base of the inversion is not at the surface, it is termed an inversion aloft. A surface-based inversion typically develops over land and on clear nights when wind is light. The ground radiates and cools much faster than the overlying air in contact with the ground and becomes cool, while the temperature a few hundred feet above it changes very little. So that's why you see here on this picture. What I was trying to explain is you have this warm pocket of air, you have this pocket of air that basically gets trapped, and our standard lapse rate, basically what happens is it gets colder as air rises. But because the warm air gets trapped under this cold air and it's trying to get out, it gets warmer as the altitude rises. It is so confusing to explain.
Okay, and so standard non-inversion, so that's going to be when low pressure overtakes high pressure. Low pressures usually
So
take
just
over
the regular,
high
the
pressures.
low pressure
Yeah.
moves over a high pressure.
Okay, so low pressures normally overtake high pressures. Okay.
Where were we at on here? Okay. Yeah. Let me think about this really quick. For some reason, I feel like I'm so wrong right now. Okay. So what happens with normal air, like I was stating before, as you climb in altitude, the air gets cooler. Because as the warm air from the surface rises, it gets cooler and cooler and cooler until it drops and starts coming back down, right? And that's where we get that rotating action is the hot air is rising, getting cold, and sinking to the earth. So what happens in a temperature inversion is when basically hot air traps a layer of cold air underneath. So instead of it getting cooler as you rise from the surface, it actually gets warmer. Does that make sense?
Okay. Yes.
So it's a complete reverse from your standard atmosphere.
So temperature inversion is just kind of when it gets trapped.
Yeah, when the air is actually cooler at the surface rather than up above. Yeah, so what I want you guys to memorize with this, let's make it clear as clear and as simple as possible. I don't want you guys to try to explain it the way I just tried to explain it. What I want you guys to say when you're asked what is temperature inversion? Temperature inversion is where a layer of cool air at the surface is overlain by a layer of warm air.
Or a layer of cool air at the surface is what?
Overlain by a layer of warm air. I'm really sorry I made that so confusing and horrible.
Oh, no, it's fine.
One more time. Is that what you
I
said?
just said, oh, no, it's fine.
Oh.
No, I said,
It's
oh,
actually
no, it's
okay that it's okay that you explained it a bunch of times because then it stuck for me too. I don't know why I needed explained to me 3 different times, but I get it now.
I
don't think it was all you. I think
fact.
it's just kind of a harder concept to wrap your head around unless you have something to look at.
Yeah. So that's all you guys need to remember about temperature inversion that I need you guys to remember. Is warm air is trapped at the surface, overlain by cold air. Boom. Simple. It's so simple, but try to explain that and I lose my mind.
Well, you just said that, obviously, you just said a second ago that cold air is overlaying by, you said that cold air at the surface is overlaying by a layer of warm air, but just now you said that the warm air was overlaying by cold air.
Sorry. The first one. So it's cold air trapped at the surface, overlain by warm air. See, like I said, I confused myself with it. Cold air at the surface, warm air up above. Super fun. I love weather. You know about evaporation. So evaporation is just basically where the water evaporates, and we have condensation, which is the clouds, right? Then we have precipitation, where it goes from.
I learned in the video that I think it said that over 30 tons of water per hour is evaporated from the ocean.
Yeah, pretty crazy. It's a lot of water. But yeah, so basically this all comes together on the charts, and we'll read the charts, but this also goes along with that weather generating, right? When you have the evaporation, then it so the liquid turns to a gas, and then it turns into a solid and falls back down to the earth. Not a solid, but a liquid back to liquid. And then you have sublimation, right? So, which is just basically when it goes from a solid to a gas. Um, so evaporation is where a liquid is changed into a gas, as we said before. And then we have condensation is where it turns from a gas into a liquid. And then precipitation is basically when it continues to condense and it turns into water droplets. Right? Sublimation is where it changes from a gas. Instead of going through a liquid phase, it changes directly into a solid. I'm sorry, from a solid into a gas rather than going through the liquid phase. So, don't really need to remember a whole lot about that. Just know that evaporation creates condensation, which turns into rain. So, we talk about dew point and temperature dew point spread a lot in aviation. So this is something that I do want to talk about and kind of cover. So let's read this definition of dew point and then the spread, because it's going to do a lot better than me trying to shorthand it. Dew point is the temperature at which an air parcel must be cooled at constant pressure and constant water vapor pressure to allow the water vapor in the parcel to condense into water. When this temperature is below 0 degrees Celsius, it is sometimes called the frost point. Lowering an air parcel's temperature reduces its capacity to hold water vapor. So dew point is basically where is water turning in? Where's this whole process happening? This evaporation, sublimation, condensation. Like, where is it occurring? At what point does it happen? Now, temperature dew point spread is the difference between an air parcel's temperature and the dew point, and its dew point is the dew point depression, or commonly referred to as the spread. Surface aviation weather reports provide observations of both temperature and dew point. The temperature greatly affects the air parcel's ability to hold water vapor. While the dew point indicates the actual quantity of water vapor in the parcel, as the spread increases, relative humidity increases. When the spread decreases to 0, relative humidity is 100% and the air parcel is saturated. So surface temperature and dew point spread is most important in anticipating fog, but has little bearing on precipitation. To support precipitation, air must be saturated through thick layers aloft. So, what all that means is, where is water changing from a gas into a solid? At what temperature is that happening? Or not gas into a solid, gas into a liquid. I'm sorry. So it's a liquid down here. It evaporates at what temperature? As I said before, it gets cooler the higher we get from the Earth's surface, right? So at what temperature does that turn in? Do the clouds start to form? Does it change back into that liquid form? That's our dew point. So when we talk about a temperature dew point spread, we're talking about
Wouldn't it be the same temperature at which a liquid turns into a gas? Wouldn't it have to go back down to that original temperature?
So basically, man, That
Like in Celsius, it would be 0 and 100, right?
um, that I don't know so much. I'm not 100% sure. Um, all I know is that when we talk a temperature and dew point spread, is at what point is that water vapor turning back into a liquid state? Um, no, I'm not sure at what temperature it requires for evaporation to occur or for the liquid to turn into a gas. I'm not 100%
Well,
sure.
for a liquid to turn into a gas, it needs to be 100 degrees Celsius. But I was just wondering, wouldn't it just be 100 degrees for gas to turn back into a liquid?
No,
Like back
um,
to 99?
I don't believe so. So
No?
I don't believe so. Um, because I know evaporation can occur below 100 degrees Celsius. I just don't know how. Yeah.
Let me
Um,
see.
but when we're talking about a temperature and a dew point spread, basically we're looking at what temperature that parcel of air is going to become saturated to the point where um, it turns back into that liquid state. So when we have a temperature dew point spread, say that, well, let's look at a METAR. Oh my gosh, that's the wrong one. There we go. Okay, so when we look at a forecast, so this is what we call a METAR. We've looked at a couple of these. And what we have here is we have what is currently occurring over Seattle. What is the weather doing over Seattle? Right here, this is called our temperature dew point spread. We can watch these numbers, say, an hour ago it was 10 degrees Celsius in Seattle, and our dew point was 1 degree 1 degree Celsius. As these 2 points converge, um, that's when we'll start seeing weather occur. So as these converge on a central point, say next hour it's 4 degrees and our dew point is 3 degrees. Basically, what's going to start happening is we're going to start seeing fog form.
Yeah, that's what I was just going to ask you was, so it's the dew point. And so the way you know that, because the pilot was telling me this, he was saying that if you hear the dew point is around the same altitude at the same altitude as your pressure altitude or some altitude, then that indicates that fog is rolling in.
Yeah. Well, so when we talk about this, we're talking about this is the conditions at the surface. So what we're looking at is we're looking at the spread at the surface. So when these two converge on each other, that's when we start to see fog form. So the altitude um, at which we start seeing cloud formations is basically when at what point does this air get cool enough to where um, the air is saturated. Does that make sense?
Yeah.
So it may be 6 degrees on the surface, but in uh, and 2 degrees Celsius on the surface, but we can actually do an equation to see where the cloud bases, where the cloud layers are formed due to this temperature and dew point spread. Where they converge. So let's see. So it kind of shows that here. So you have, actual gram of water vapor versus a potential gram. As they converge, as these two numbers converge, you can see the air becomes saturated with only that water vapor.
I was way overthinking that when I got to thinking about the temperatures and stuff. I just looked it up. Water can evaporate at any temperature, even ice can evaporate. I don't know why I was so far down the rabbit hole with that when I was thinking about it.
Yeah, in fact, that's what sublimation is, right? Is the change
Yeah.
from a solid to a gas. So
Yeah, it just said with enough energy, anything can
yeah,
evaporate.
yeah,
Just thought I'd clear that up. I know what boiling is, and I know what evaporation is, and I know that they're different. I don't know. Yeah, my brain's fried. I'm sorry.
no, I completely understand. You've seen me stumble over myself plenty of times tonight trying to explain something, and it's not
Just
as easy as,
overthinking things, and
yeah,
yeah,
it's not as easy as it looks sometimes.
yeah.
So, um, so all of that kind of comes to the cloud section here. So we are going to learn our cloud types, right? We've got, these are the absolute most basic cloud forms. Now there's like, I guess clouds were named, I think it's a Latin word meaning rain. So there's two parts, just like any scientific term, there's two parts to every word here. We've got cirrus clouds. So cirrus clouds are basically we call them mare's tails. They're high altitude clouds that are just really wispy and light, but kind of create that just bands of clouds that are long lasting. I don't know how to explain it. They go over a larger area, but they're really thin and wispy. When we have nimbus clouds, we're talking about clouds bearing rain. We have also cumuliform clouds. So they're just those really thick, heavy, like fluffy clouds. Like it says here, they look like fluffy cotton balls. Then we have stratiform clouds, and they're the ones that are they're not as fluffy. They're just kind of like like it says here, a layer or blanket. So cloud levels. Again, we can figure out where the levels of the clouds are going to be depending on the temperature and dew point spread, or where that actual conversion from the gaseous state to a liquid state happens. So the clouds are divided by a type, or so we have the cirrus, the cirrocumulus, and then the cirrostratus. So we kind of talked about this up here. The cirrus clouds are it's a cloud type composed of detached cirriform elements in the form of white, delicate filaments of white. This is what the cirrus clouds look like, and you can see why we call them mare's tails. They're just really light, wispy clouds at high altitudes. Typically, we see these clouds form a lot with high winds, which kind of explains why they're so wispy and light. When you have those high winds, it basically is just, it's kind of like cotton candy. I don't know how to explain it, but yeah, it's not a really heavy concentration of clouds, and it's being spread out by the high winds. Yeah, here it says cirrus clouds in themselves have little effect on aircraft and contain no significant turbulence or icing. So, cirrocumulus clouds is a cirriform cloud type, appearing as a thin white patch, sheet or layer of clouds without shading, and is, yeah, looks like that basically. So when we see these are dangerous clouds for aircraft because of these supercooled droplets. Very high potential of icing in these clouds. Also, turbulence is also associated with this cloud type. We fly through them all the time, but in the same breath, because of the icing and stuff, we have the anti-ice on our aircraft, but they can be potentially hazardous due to those supercooled liquid droplets, which basically they can really affect the aerodynamics of the airplane pretty quickly. So cirrostratus clouds is a cloud type appearing as a whitish veil. So here you can see those cirrostratus. We talked about the cumulus clouds and how they're really thick and puffy. Stratus clouds tend to be that, just kind of like a dense blanket. Not a whole lot of rising action in those clouds. So middle clouds. So cirrus means high altitude. So cirrocumulus, again, it's a cumulus cloud at high altitude. Cirrus, cirrostratus. Oh, sorry. So yeah, so cirrocumulus is this. They're a little more dense clouds, but they're high altitude. The cirrus clouds are just high altitude clouds, right? And then the cirrostratus is just like that high altitude blanket. Our middle clouds are called alto. And once again, you have altocumulus, altostratus, and nimbostratus. So altocumulus is going to be like that really heavy cloud again. Stratus, once again, is just kind of those thick. They're more of like a blanket shape. When I think of cumulus, I think of like really tall, fluffy clouds. When I think of stratus, I just think of kind of like it says, a blanket. And then nimbo, whenever you hear nimbo, it is talking about rain bearing. So, so this is what these clouds look like. So the altocumulus clouds, again, really fluffy, look like cotton balls. And cumulus clouds, the reason why they're so fluffy is because there tends to be a lot more rising action or convection in those clouds, which causes it. And they're the clouds we associate with. Cumulus clouds are what we associate turbulence with. Stratus clouds are just stable, so they typically don't tend to be a huge problem for pilots. So altocumulus lenticulars. So lenticular clouds, think of them as like a lens, right? We tend to see these altocumulus standing lenticular clouds. These are very dangerous clouds. They're associated with mountain wave and basically high winds coming over the mountain peaks. You're always going to see them on the leeward side of the mountain. When we talk windward and leeward side of a mountain, windward is the side of the mountain that's getting hit by the winds. And if you remember, our winds tend to travel from a west to an east. So our windward sides is basically this west side of the mountain that's getting impacted by the winds. The leeward is where that wind is dissipated and basically just kind of falls off. Well, what happens is when we have these standing lenticular clouds, the air is rising really rapidly over the top of the mountain. So you got really high winds that are rising and coming up over this mountain ridge and hitting a stable pocket of air. So what happens is it creates this cloud shape.
They're so pretty.
Yeah, they're really pretty but really dangerous. If you see these, it's like you're in for a bumpy ride. Yvonne, did you just barely say no? I'm really sorry, I didn't see that comment you left, so I'm not exactly sure what your comment was about, but
that had to do with the inversions. I was just wondering, because with the inversions, it seems like there's like a lot of pollution. I know it happens here in Arizona, and I know it happens in Salt Lake. So I didn't know if those inversions happen more in larger cities.
I wouldn't necessarily say that the city has so much to do with it. It's the surrounding environment. So it's more like we get a lot of temperatures in the Salt Lake Valley due to the mountains that surround the valley. Just that it creates that bowl shape, basically, that traps that pocket of colder air at the surface. So I don't know that it's necessarily associated with the city, but yeah, Salt Lake has it really bad. LA gets it pretty bad. So, and I've been to Phoenix like twice in my entire life. So yeah.
Thank you.
Yeah.
You probably just notice it more in cities because of the pollution. Like it's more noticeable to you.
Yeah. Yeah, that's probably a lot of it. A lot of the reason why Salt Lake stands out so bad to me, but mostly because I had to breathe that disgusting air in for so long. But anyways, yeah, when we see these altocumulus standing lenticulars, they'll actually put these in our forecasts. And yeah, what happens is you'll also get what we call rotor clouds down here below. And it's basically a cloud. You can sit there and watch it spin like a washing machine on the backside of the mountain here. So you'll see these, and this is where the air is rising and then drops and then it rises again. So you can see that wave formation, and that's what we call mountain wave turbulence too. Has anybody ever been in mountain wave turbulence? I
believe I would have been. You mean during a flight?
Oh, you definitely know if you'd been in mountain wave turbulence. So what happens in mountain wave turbulence? Like regular turbulence, you just kind of get jostled around, right? It's bumpy. It feels like you're driving down a dirt road really fast. Well, mountain wave turbulence is like a roller coaster ride. The plane will climb
that's happened to me.
extremely fast, and then it just drops out of the sky, and then it climbs really fast, and then it drops, and then it climbs and drops, just like it's riding a wave. So
yeah, that's happened to me once.
Yeah, it's not so fun, but altostratus. This is typically what I think of when I think of like rainstorms in Salt Lake City. This is, or not rainstorms. I'm sorry, but like just a normal day in Salt Lake City is we get a lot of these altostratus, and kind of what it is just a thick blanket of clouds over the valley. And it just creates that ceiling. And yeah, I mean that's typically what you see in Salt Lake City is these altostratus. You see a lot of cumulus clouds as well, and in the summertime, we can get some pretty incredible cumulonimbus clouds as well. But nimbostratus is just, like I said, nimbo just means rain. So when we have a nimbostratus, it's just a stable cloud that just, it's raining or snowing. Whereas like, you can't even, these pictures suck. Well, this is a gray sky. Looks just like this gray sky, but they're different cloud types. Let me pull up a better picture.
But they look the same.
Exactly.
While you're looking that up, I remember a long time ago, many times flying up from the Mesquite, kind of that south desert up through the St. George area towards Cedar City, and right about on the south side of the the mountains as you come up out of the gorge by car, well, those ridges of those mountains right there, we call them the barf ridge, because it is just all you can do to keep your lunch down. You're just ascending and descending by hundreds of feet at a time, and it's just unbelievably nauseating to get over. So
yeah, that's that mountain wave turbulence. It's pretty incredible stuff. So this is a better kind of a side profile of these clouds. We talked about the cirrus clouds. We talked about the cirrocumulus. We also talked about the cirrostratus clouds. Once again, cirrus or cirro just means high altitude. When we talk about alto, that's a mid-level cloud. And we talked about the altocumulus versus the altostratus. So when we talk about stratocumulus clouds, we're talking about a low-level cloud. These are the ones that that we tend to see more in the summertime. We can see them in the wintertime as well, but once again, they've got that real flat bottom, but then the really puffy tops that look like cotton balls. But it's a thinner layer of clouds. Now, stratus clouds are just, as I said before, cumulus cloud tends to be a thicker, more fluffy cloud due to the circulation of air. So the air's rising and dropping and rising and dropping and rising and dropping, creating that rotation. And that's why they get puffy. Stratus clouds just are stable air, so they're just kind of like slugs in the sky, and they look like just a smooth blanket. Cumulus clouds, when you just have a regular cumulus cloud, that's just talking about the cumulus, that fluffy cloud is below 6,000 feet. So these cumulus clouds, and the stratus clouds, when you hear somebody like a nimbostratus or cumulonimbus, that's a little bit different, but nimbo just means that it's rain bearing, like we said before. Now, when we talk about cumulonimbus, these are the extremely dangerous clouds. Because what's happening is, and this is where your thunderstorms, this is the cloud that we associate with our thunderstorms. We also call them anvil tops in aviation a lot. But what's happening is you're getting a huge amount of convection happening. So the surface is extremely hot. We tend to see these in the summertime because it takes a lot of convection, a lot of really rapidly rising air to create these clouds. And these clouds can go from this, anywhere from, the 6,000 feet or lower all the way up to 50, 60, 70,000 feet in the air, depending on where the troposphere is.
Do you want us to jot the altitude of any of these clouds down?
No, not so much. Just know that cirro or cirrus is high altitude clouds. Alto is mid-level, and then strato typically means low level. And then the main types are cumulus and stratus. Does that make sense?
Yeah.
Stratus is stable. Cumulus is unstable. Cumulonimbus clouds, like I was saying, they because of that amount of air that is rising and falling so rapidly, that's what's creating all that electrical energy to create the lightning, and it's also you get hail associated with these types of clouds because the water is warming up, rising really rapidly, cooling off, freezing, coming back down, and then cooling up before it can evaporate all the way. It's already rising again and freezing, coming back down, and it'll just sit there and go through the cycle until the cloud can't hold the weight anymore, and then it spits it out the bottom. But super dangerous clouds. When we see these in aviation, basically we have to route. We can't get within 20 miles of these clouds because of the amount of turbulence that they produce.
My instructor always told us those are the silver devils. You never try and punch through those, or you won't come out with your wings.
Yeah.
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 I always think tornadoes.
Yeah, and it's really sad that, I mean, how much did I seriously close out of our Google Drive? Oops. It's like crazy to think about how much power those have, let's see. Oh my goodness. So I showed you guys this aircraft before. He got a little too close to thunderstorm and encountered hail. But yeah, looks like the same thing here. He got into some hail. But that's all this damage is due to being too close to those thunderstorms. They'll pick up planes and spit them out so fast. It's not even funny. Extremely dangerous to be around. You know.
Just this last summer, I was on a SkyWest flight, and they were just doing kind of meandering left and right turns around those type of clouds. And it was, I had to put on my sunglasses. It was just so bright. The silver, it was just beautiful. I mean, but you could see how fast they were moving up relative to even the aircraft speed. They were going faster than the plane, just straight up, just boiling up. And I thought, man, that'd just be, I bet that's a ride.
Yeah. Yeah, sadly, a lot of people that go into them don't come out the other side. It's pretty rare that an aircraft actually makes it through. And a lot of these planes, I mean, these pictures that you're seeing, they just came close. I mean, they didn't actually go through the storm, you know. A lot of these aircraft are just, they were too close to it. And the winds and the speed of the updrafts and downdrafts just chew up an airplane and spit it out. So, but yeah, so those are our cloud types. That's kind of what I wanted to go through. So yeah, I mean, oh my gosh, these pictures are horrible. So yes, this is a towering cumulus cloud. This is one forming, but you can't, like, that doesn't even do it justice. That looks not all that bad. So this is a better picture of a cumulonimbus cloud. So this isn't the towering cumulonimbus. As you can see, the towering cumulonimbus will basically begin to spread at the top. It'll go through like a narrow band and then it'll spread at the top. But this is a pretty heavy storm. There you go. This is our towering cumulonimbus, or the anvil top. You can see why we call it an anvil top. But extreme amount of turbulence. And as I said before, a lot of times when we have like cumulus clouds or cumulonimbus clouds, the aircraft can climb over the top of them. When you have this kind of convective activity, there's no way an aircraft is going to be able to climb over them because, like I said before, a lot of times these clouds are going up 40, 50, 60 plus thousand feet before they top out. And so there's just no way to get around these storms, so we have to go around them. You can't get over them, you go around them. And I don't know that you'd want to be over the top of them just simply due to the amount of convection that's happening over them. So, Let's take a 10-minute break. Let's just come back on at 9 or 8:45. So
It is 8:45. You mean 9 o'clock?
that's what I said. 9:45 or 8:55. I need to go to bed. 8:55, and we'll finish it off here. All right. Okay, so let's talk about precipitation really quick. So there's a couple things that have to happen for precipitation to actually start occurring. There has to be water vapor lift, and then and the lift is what sufficient lift to condense water into water vapor into clouds, right? And then there's a growth process that allows the cloud droplets to grow and get heavy enough to fall as precipitation. So the growth process, as it says here, is all clouds contain water, but only some actually produce precipitation. So because of the size of the water droplets, basically there has to be that action of rising and falling inside the cloud that allows the droplet to grow to a size which allows it to finally get heavy enough to drop out of the bottom of the cloud. So this just kind of shows you, the bigger the raindrop it can collect, it can continue as it's passing through the cloud, it can continue to collect the water droplets around it until it finally gets too big, then it will split apart. But you got several different types of precipitation. Snow, sleet, hail. This just kind of goes through how those form. So, all of this being said, with the precipitation and things of that nature, kind of to, we've now talked about how all of this starts to happen, how all this weather starts to occur. What we're going to start talking about here over the next couple of days is tomorrow we're going to talk about like fog and ice and the different types of ice that we can see. And then we're going to talk about stability and instability. So we're going to talk about like the adiabatic process and then we'll talk a little bit about turbulence. But all of this is going to kind of converge eventually to where we're going to start looking at this stuff online and just start getting weather reports, looking at all of our different weather charts. As you guys can see on my screen here, let's see if I can zoom out a little bit. So these are all of our different types of aviation charts, and you can see how many there are. They all are giving us different types of information. And we'll start reading them. A lot of the symbols that we see on these charts just will translate across the board. Like this, talking about the highs and the lows and the different fronts. So, like this is called a cold front. This is called an occluded front. These sections of the high, right? Those are called. These sections of red with the lump instead of an icicle. Think of it as the sun, so that's a warm front. these parts of the blue lines with the icicle forming, think of that as a cold front. So when we have a warm and a cold front converging, we call that an occluded front. We call these areas troughs or areas of elongated low pressures, right? We kind of talked about all of that tonight, but we'll start going through these charts and start learning how to read and understand what's going on with the weather with these charts. We've also got radar that we can look at. We can look at the satellite imagery. Anyways, we also have different charts than just these ones that give us more of a forecast of what's going to happen. Just to kind of go through what we do and how this is all going to come together eventually as we go through all of those charts. Every morning, like I was saying, we have these different weather alerts that we can look at and just kind of take note of different requirements. This is the actual status board that we use when at work, but it just tells us of different things that are going on that we look at and have to put together. This WSI is our weather source, our approved weather source that we use to get our weather from. This is basically what our map looks like at work. On the program we use for all of our flights, it's this, and then overlaid on top of that is our aircraft, so that we can see them and route them around weather or turbulence and things of that nature. But not only will we be reading these charts, but we're also going to start reading the text. So we'll start going through these PIREPs and METARs, SIGMETs, AIRMETs. And we'll start teaching you guys how to translate the mess of information that we get here. Just to kind of give you guys an understanding of what we're going to be doing over the next 2 weeks before we start our flight planning fun goodness that I love to do. I actually really do like flight planning quite a bit, because it kind of puts everything that you've learned into something practical that we can see and do. But yeah, so we'll start going through these and start applying them to what everything that we're learning to all of this information. Yeah. Do you guys have any questions about anything that we've learned so far tonight? Do you guys questions, comments, anything fun to talk about? Or
is there anything that you wanted us to jot down other than, sorry if you're having a hard time hearing me, is there anything you wanted us to jot down other than the difference between like the high and low pressures and the temperature inversions and the different gases that make up the air and sea level pressure?
No, that's what's what was that? Oh,
sorry.
Oh, you're fine.
That was my boyfriend gaming in the background.
Oh, nice.
Uh,
Um,
I'm sorry.
you're fine.
Anything other than
That
those right there?
that pretty much covers it. Um,
Okay.
it, like I said, a lot of the science behind what creates the weather, we don't like. We go over it really quick like that, but we don't necessarily have to test you guys on it or
Gotcha.
or know about it. The things that I had you write down are the things that are pertinent that we will test you on and talk about. But let me go back in here. As you can see, we'll in our outline we talked about all of this today.
Hmm.
Kind of hit the high points really. I really strongly advise you guys to look over that advisory circular that we went through tonight and just read through it. It's not the easiest to read through, but just I hit the high points, but if you want a better understanding of everything that's going on, just go through that. Uh, it's
There's lots of really cool documentaries online too, as far as like all of this like weather and
yeah, what it's
different way. All the
yeah, that's another great
is
source. Go on YouTube, look up uh, weather videos. Um, like I said, I continue to learn about weather every single day, especially as I go to work. You start to learn the intricacies of how the weather flows, and how it all kind of works. Um, you you kind of get a it's weird how it starts making more and more sense, and how we can start actually predicting the weather at times better than your local weatherman. um, but yeah, we'll continue to talk about this stuff. But then, like it shows on the course outline, we go through the theory of it, the theory of the weather. But then once we hit um, day 2 next week, that's when we start looking at these different charts and start really talking about them and breaking them down. Um, this is something that we really need to focus on is these charts. It's extremely important being able to decode and understand what these charts are telling us. Um, like I said, it's a huge part of our job. Um, and it's a big part of just getting a job in general. Once we get out of this class, you're asked to read weather, um, you know, in interviews and things like that, and decode METARs and TAFs and PIREPs and NOTAMs and all of that, in order to display that you have an understanding of how this all works and how it all comes together. Like I said, the science part of it isn't as big of a focus, but actually interpreting the data that's spit out by the weather reports. That's where we really need to focus. But man,
I'm so excited.
we are getting so close, so close to being done.
Yeah, guys, we're halfway.
Yeah. This is where things are going to start picking up. It's not going to be, it's slowly going to start turning into an interactive class rather than a sit and listen to me lecture for 4 hours every night. And believe me, I'm like not too fond of listening to myself talk for 4 hours, so I understand if you guys are completely bored out of your minds, but we're going to start really getting into the practical side of this rather than theory. And I really hope that's where we start getting interaction. Like our weight and balance charts, that class flew by. Like, we got through those 4 hours. It felt like we'd only been online for like an hour. At least it did to me.
Yeah, that was cool.
Hopefully those classes become a regular routine for us as we get ready for our flight planning. I'm going to have you guys start. We're going to go through, how do I read this? How do I interpret this? And then you guys are going to take turns interpreting it. And then we're going to take stuff from the first week where we talked about, like, what are our minimums? What are our are we legal to dispatch? Or do we need an alternate? Things like that. We're going to start applying it once you guys get an understanding of how to interpret the data. We're going to start throwing, like, are we legal to dispatch this flight now, and start making it a lot more practical to you as a dispatcher. So, well, we're a little ahead of schedule tonight, but we'll just call it a night tonight, unless you guys have something that you want to talk about or bring up, and then, yeah.
All right, have a good night.
All right.
Thanks.
Yeah.
Thanks, Garrett,
Yep,
for everything.
thanks.